All right, in today's class, we're going to do the LSTM, long-short time memory model. It's part of the deep learning model. It's actually part of the Keras model. So we have the different layers. One of them layer is called LSTM, and so that's what we're gonna do today. So ideally, you can use this. It's part of the neural networks, and you can use it to predict some sequential patterns. And so the basic idea is you have input sequence and then you put it into layers. So this could be layer 1, layer 2, and for layer 1 you're going to give some random weights, and then you carry that with this layer and you get a prediction of y's value, and then you're going to use that y's value with the real target. This is x and y is a pair, and so that's the real value of y. So this is predicted y, and then you compare this two, that will give you the arrow. So if the arrow is big, then we're going to actually, you get the arrow. The arrow is calculated by the loss function. It's actually a formula. How do you determine the arrow? There are several ways to do, several famous functions. One of them is absolute arrow. Second one is like square mean, and then you have others like entropy. So with those, you calculate an arrow, which is the loss score. The loss score will be sent to the optimizer. The optimizer will going to update the weights to a certain way, and then send to layer again, and then do the prediction. You get another y. So you compare with the real y. You calculate a loss score by loss function, and then send back to the optimizer. Now the optimizer is going to compare with your previous update. Is this loss smaller or bigger? If this loss is going bigger, that means say, oh no, we're on the wrong way. We're going to go update the weights in the opposite way. So we send the layers and then predict, and again do get another loss score. If this time the loss score to optimizer is smaller, then the optimizer is going to say, oh yeah, we're on the right track. So let's keep on updating the weights in the same direction. So keep on doing this loop with all the x and y's. That's called one epoch. So with that epoch, we actually get one iteration or one epoch. So you are going to do like many of them, like 500 or 1000, 2000 epoch. So eventually you get the weights optimized. That's going to be the best fit, and the loss score will be minimal. So we call that converged, and then the whole training process is done. So all the weights are ready to use. And then you can predict any coming new data, unknown data. You can predict the y, and this is going to be close to 0 errors. So that will be your best outcome. So that's the whole process of data mining. And actually, if you want, you actually can take a look of this one. So ideally, what you can do is this website is called playgroundtensorflow.org. So it's give you all kinds of possible ways to play the main parameters, like learning rate, activation, all of those, and then different layers. So for the whole TensorFlow is built on neural networks. each of those each of those nodes are called a neuron. A neuron is like a certain logic, certain calculation logic you can compute. So it's like just the one processing units. And then what we do is we have the input as x1, y1, or x1, x2. We pass those values to the neurons. Then we can have multiple layers. The default one is normally is like for most of the cases is 2 layers. For some cases we only have 1 layers, like linear regression, for example, is you only have 1 layers, or logic regression, you only have 1 layers, and then you get results. So that's once you get the input, you have layers, and then once you process all the data, it's going to give you the outcome, which is output layer. So input layer, output layer, in the middle is the hidden layers. And then you can change different of those. Let's just play one of them. Let's say we do classification. So you clearly see that there are 2 sets of data. This is one, and this is another set. So the idea is we're going to classify the 2 sets of data, and we're going to see how to do it. So in this case, I'm just doing, let's say, 2 layers. Normally is the second layer. So this is default setting. The first layer has 3 neurons. The second layer has 2 neurons. And then you calculate, and eventually you're going to supposed to get the classification. So you can change those. Normally the learning rate, if the learning rate is big, you can ideally you can converge faster. However, when the learning rate is too big, you will never find the optima, because you bounce back and forth. You never actually going down to the real optimized points. Well, if the learning rate is too small, very likely you may reach to a local optimized parameters without finding the global lowest points. So sometimes you gotta just keep trying with different learning rate, and others like the noises and batch size, they may also change the learning process. So in this example, you can tell that we have 2 layers, and then you can simply click run. You can see this is quickly change the output. That's called a loss. It's actually the error functions. So you're gonna see the outcome. It's getting there. Oh. And it's taking a while. So I'm gonna stop here, and I'm gonna change this. I'm gonna add more layers. So this time, let me run it again. You will see that this is doing the classification much quicker. You see that? It's immediately find it. So it really matters, if you put it in the right or wrong settings. It may end. So this is your loss of all those process of all the epoch. You see that the loss sharply dropped down to 0, close to 0. So that means we find it's converged. So that means it's a good training. And this is the basic idea. Again, please feel free to play with this. And so come back here. Our task is basically we're going to get a sequence of letters, and then we're going to doing the mapping. For example, one letter mapped to another letter. So you doing this kind of mapping. The task is if I give the sequence to those layers, and can we actually predict the outcome as one character? So let's do experiment with just the one character mapped to another character. So speaking of that, there's A mapped to B, B mapped to C, C mapped to D, and all the way. So basically is mapped to the next character on ASCII code. And let's see how do we make this and use the Keras. Okay. And so here is the import the Keras and other classes, and then we generate a random seed. The random seed is just to give us a constant value, so we can repeat the random values. And then this is actually give us a alphabet letters. This will generate a bunch of dictionary between the characters and the integer, and this one is integer to character, and then you can print it out the results. The A is 0, B is 1, and the number to letters is going to be 0 to A, 1 to B. So with that preparation, we can actually generate some mapping. So we can run this code. You can get a sequence in, sequence out. So this sequence in give you A, then sequence out is supposed to be B. So this is the algorithm, right? So you have this results, and then we simply just make it like data X and data Y for the characters, and that's the data we prepared for this lab. So the data is actually man-made. It's created by the computer. And now let's prepare the actual X and Y for the LST model. So first of all, we're going to reshape this model as this kind of format as a sample, time step, and a feature. So for the first time, I'm going to say, okay, since we only have one feature and one mapping, I'm going to use every time I'm going to just move to one step. So that would be N11 supposedly. So here we have the N, the sequence length is 1. It should be defined somewhere here. Sequence length is 1, and we are using the 1, and then here is 1. So N11. And then we normalize we do the normalization. Normalization is to overcome some of the sometimes the big numbers can dominate and wipe out the effect of the small numbers. For example, you have a feature that is ranging the data ranging from 0 to 1, and another feature that has a much bigger range of data that is from, let's say, 10 to 1000. If we don't do the normalization, the bigger data range, since their range is big, any change will wipe out the change of between the 0 to 1, the feature that has 0 to 1. So it's you don't see the full picture, you don't see the truth. Therefore, you have to it's better just normalize the data in the same range, so they have the same effect to the change. So normalization, we do that, and then we get one hot encoding. This is basically just one of the categorical for the utility. Is a classical one. If you're not familiar with this, just do some research and you can find it. And then you can get the X shape and a Y shape. Now you're going to see that our X shape has 25 samples, and we have one training step and one feature every time. And Y shape, you have 25 and 26 of the shape. The building model, now once we have that, we're going to build the model. So the step 1 is actually make a sequential model. The step 2 is add. So we're going to add the model, add layers. So one is the STM. The other one is the dense layer. And here the dense model is like the second layer. We're going to basically doing the activation. It's going to be softmax. Softmax is it's kind of like give each category a probability to find how similar to those categories. So again, this is another concept. If you want, you can actually see one of the references on the units 15. And here we're going to see the summary of the model. So basically it shows you how many parameters we're going to train. We're going to assign values to those parameters. And so that will give you results. We have 5,000 parameters. And therefore we're going to define our model further by defining the loss function. The loss function is going to be something like this. It's calculated loss. And then we're using categorical cross entropy. This is a classic loss function. Again, I have used before absolute arrows, and also the mean square is another one. Mean square arrow is another one. It's often used too, especially for sequential data. And then we have the optimizer, which is Adam. And Adam is I forgot exactly what's the name. I think it's adaptive moment. I think it's adaptive moment model. Again, it's a classic one that has the momentum to overcome some of the local bellies, and so it's a good one to use. And then metrics, here we're only interested about the accuracy. So it's going to give us how accurately we can predict the class or the category. And then here the fit is actually the step, the method that's actually doing the training. So I have X and I have Y. Y is going to be the label. And the epochs is 500. And the batch size is 1, verbose is 2. So those are the parameters, and once you run this, you're going to see the outcome. At the beginning, the arrow is actually pretty big, and while the epoch is running, it's become smaller. See, at the beginning, it's like the loss is 3 point something, and then it's actually dropped down pretty quickly to eventually to 1 or even less than 1. So in this case, it's about 1.6, and our accuracy is somehow increased to 84% accurate. So if you overall, the accuracy is about 80% accurate. We print it out by just use model.evaluate x and y verbose is 0, and then it's going to give you the score. Score 0 is accuracy. It's going to give you 100. Multiply 100, that's 80%. And then we can do prediction now. Since we are going to have we reshaped the NumPy values. We're going to take out all the 26 letters for the prediction. So simply just to get all those numbers, and then we're going to define the pattern, define the shape. So that's going to be X. Then here we do the normalization as well. And then we pass the new X to the prediction, to the model we predicted. And that will be our prediction. Then we can actually see how well this prediction is doing by just get the maximum probability of the index of each of them. And then this is the index. And then we can just find the results. And then and print out the sequence in and sequence out, or the results, sequence in and results. You will find it's pretty interesting that sometimes you get the wrong prediction, like B is supposed to give you C give you D, and at end, this is another good example. It's not predicting very well. So you will notice that this is not it's kind of poorly predicted, because the here you only have one feature to give the model, which is not this kind of model is good at it. It's supposedly you should give some context to the model so the model can predict it better. With that in mind, then let's modify this experiment and do example 2. So this time we're going to do 3 characters mapping to 1 character, and then we do this by preparing the data, by simply just preparing this kind of data as this A, B, C, C, D, E, and then we get the same pattern, right? The pattern is we're going to go to next letter after this one, like VX, X, it's going to be Y, Y is next letter is going to be Z. So that's the pattern. And however, the computer does not know. We're supposed to ask the computer to figure out the pattern. And so here's where redefine the shape. The shape in this case, you may say, since I have 3 characters, that will be my 3 features. So I'm going to do the temp step is 1 and feature is 3. And then I will just doing the same thing, normalization, and then do the 1 hot encode, and then give me the X and Y shape. And then I will rebuild the model by just using sequential and doing the same thing, exactly same thing. And we'll see. And this model is actually give us parameters, a little bit more parameters. And when we do the training, you will notice that the percentage is actually, for loss, is drop, and the accuracy is actually increased, and it's improved the accuracy a little bit, but not significant. It's from 80% to 86%, 87%. And if you use that to predict, you still see some errors, like for example here, all of them UVW. Then this is supposed to be X, and this is supposed to be Y. It's mistakenly predicting. This is another example. So you notice that this is kind of like not that much well. And so we're going to give more context to the network to perform the time step. So instead of changing the features, we're going to say, okay, what if I change the time step? So we're going to change the sequence length as 3. So the time step, it's going to be 3, and the feature, we treated all of them as just the 1 feature. Let's see what that will be. So by doing that, we just reshape. Watch this. This is N, and then sequence length is 3. This is 1. In the previous example, it's actually 113 in here. You will notice that this is the N13. So this is N, this is 1, this is 3. So it's like N13. And now it's N31. So here we are actually doing N31. So N3 and 1. Then sequence length is defined right here. It's 3. Okay. So N3, 1. So that means our temp steps is going to be 3. And then let's do this again, exactly same thing, normalized X, and then here you get 1 hot encoding, and then you define the model, it's the same model, and you will notice the parameter is 5210. And you do the training, it's the same loss function, same optimizer, and same metrics, you do the training. And this time you're going to find the accuracy now all of a sudden becomes much, much better. It's 100% accurate. And you use this to predict. It's give you very good results, and it's all of a sudden it's 100% accurate. So with this, you will see this is a pretty good example. What if we have a very varied sequence we do in this kind of mapping, right? So it's the same thing. No matter what the previous one is, this mapping is going to be the next character. Same thing, OP, QR, and you do the same thing mapping. And suppose our max length of this those characters will be 5. So from 1 to 5. And then we do another experiment. We will see if this LSTM is going to predict that very accurately. So let's try that. So we prepare some random characters. This kind of mapping, we prepare that, and then we're going to prepare our X and Y. So in this one, I'm going to reshape this one. So before we reshape it, we got to make sure that they're in the same length. So to do that, we simply just pad the sequence with zeros. So like in this one, X, then I'm going to pad 4 zeros. It becomes X0000, M0000. And this has 3 already, then I'm going to pack 2, 00. So OPQ 00. So that's going to be, all of them has this exactly same 5 characters now. And now I'm going to use that as a uniformed one, and then we will do the reshape. This time I'm going to do N, and this is actually 5, right? Max length is actually 5. We defined it at the beginning. Max length is 5. It's right here. Max length is 5. So N51 is it's gonna be our reshape training tuples. So sample is N, step is 5, features is 1. We normalized and then get one hot encode and define the models. Add 2 layers and do the summary. Now our parameters is a 5210, and when we do the training, you're going to see that after the training, our accuracy is about 98% accurate, which is very good, which is not bad at all. But this way, this training takes much longer time than the 3 examples. After all, you are going to get the trained model. Once you get the trained model, you can predict it by doing this kind of training. Predicting, you will find it's pretty accurate. It's not perfect, but it's already very well done. So in those 4 examples, we basically learned how to use LSTM as a neural network to predict sequential numbers, sequence numbers, especially mapping and things like that. So our next task is can we, with this understanding, doing a time series predicting. So that's actually part of our assignments, and that's all for this video.